If you've ever found yourself wondering how data actually manages to find its way through the massive, confusing labyrinth of corporate networks, well, you are in exactly the right place.
We've got a lot of ground to cover today, from meeting OSPF and understanding how it calculates trust, to making network neighbors, handling updates efficiently, and finally, scaling the whole thing up with areas. Let's just jump right in. So, here's the big question. How do massive networks know exactly where to send your data? I mean, manually managing thousands of routes is, well, it's a total nightmare, right? Imagine having to sit there and type out every single turn a piece of data needs to take to get from a branch office in Mumbai to a server in London. Yeah, no thanks. It's just not sustainable. That's exactly where dynamic routing swoops in to save the day. It takes all that heavy lifting completely off your shoulders. Instead of the massive administrative overhead of static, manual routing, dynamic routing automates the math. It scales effortlessly because the network literally learns and figures out the best paths entirely on its own. Let's officially meet the star of the show, OSPF, our dynamic solution.
Now, OSPF stands for Open Shortest Path First. It's an open-source, dynamic, interior gateway protocol. But the real takeaway here? It operates strictly inside one organization's logical boundary, what we call an autonomous system. Think of it as the central brain running your internal corporate network, not the protocol connecting you to the Wild West of the public internet.
Moving on to how this brain actually makes decisions. Let's talk about trust and cost. When multiple routes pop up, how does a router actually pick the winner? Well, it all starts with the number 110. That's OSPF's administrative distance, or AD. In the networking world, AD is basically a trust score from 0 to 255, and the golden rule? Lower is always better. So 110 is OSPF's default badge of honor. Think of it this way. If you need directions, you're going to trust your uncle who's actually driven the route before rather than some random stranger on the street, right? Routers do the exact same thing. If it gets a path from the RIP protocol, which has an AD of 120, and gets that same path from OSPF at 110, it's going with OSPF every single time. It's the trusted uncle of the network.
But yeah, trust is really just half the battle. How do they actually judge the road itself? Older protocols like RIP just count hops, literally just the raw number of routers you jump across from A to B. OSPF is way smarter. It calculates a link cost based purely on interface bandwidth.
It's kind of like a jury panel, where every protocol judges the best path totally differently. RIP might vote for a route just because it has fewer jumps, even if those jumps are over painfully slow dial-up lines. OSPF, on the other hand, cares about speed. It will happily bounce your traffic through 5 blazing fast fiber optic links rather than one sluggish copper line. It's all about that bandwidth efficiency.
Okay, so how do these routers actually talk to each other to make this happen? Let's get into making neighbors.
The literal second you turn OSPF on, your router joins this very specific multicast IP address, 224.0.0.5. Think of it as an exclusive VIP radio channel. Once it's tuned in, the router just starts blasting out "hello" packets, trying to find nearby friends and announce it's ready to mingle.
But listen, they can't just buddy up with anyone. They have to match a really strict set of criteria in those hello packets. We're talking the exact same area ID and subnet, perfectly matching hello and dead timers, usually 10 seconds for hello and 40 seconds before calling a neighbor dead, matching security authentication, matching MT2 sizes, and they absolutely must have unique router IDs. If even one of those doesn't line up, no handshake, no neighborhood, no data sharing, period.
Now, once they do match up securely and become neighbors, they get to work building 3 absolutely vital tables. First up, the neighbor table, tracking all those directly connected friends. Then they swap link state data to build massive network maps stored in the database table, or LSDB. And finally, OSPF crunches the numbers, filters out all the noise, and puts only the absolute best, fastest paths into the routing table for actual traffic. It's brilliant. All right, let's talk about efficiency. What happens when things actually change on the network? Because this is a huge deal. In massive corporate networks, links are constantly bouncing up and down. If every single router screamed its entire routing table out loud every time one little link flickered, the network would just absolutely choke on the update traffic. It would be totally paralyzing. To fix that, routers on large shared networks hold an election for a designated router, or DR. It's such a simple but genius fix. When a link changes, the router that sees it only whispers it to the DR. Then the DR turns around and accesses the single organized voice to update everyone else. It totally cuts out the clutter and stops thousands of redundant messages from flooding the system.
Think about it like the intro to this very explainer. I'm not going to pause and reintroduce myself every 5 minutes, right? I only speak up if there's a massive change in the topic. Older protocols used to just blindly send full periodic updates of everything. OSPF doesn't do that. It uses triggered partial updates. It stays perfectly quiet until something actually changes, and then it only ever announces that one specific detail exactly when it happens. Super efficient.
Finally, let's look at how we scale this whole thing up into a massive empire using areas.
When you break a network down into OSPF areas, you're essentially building a government structure. You've got a central government handling the macro stuff and state governments dealing with the local day-to-day. For OSPF, it means a router only has to memorize the heavy, detailed database for its own local area. It literally saves routers from buckling under the pressure of running out of memory or processing power when the network grows huge.
And the absolute anchor of this entire design is Area 0, the backbone. OSPF architecture strictly demands that every single regular branch area, like Area 1, Area 2, whatever, must connect directly to this backbone, either physically or logically. It is the ultimate headquarters.
This is where the Area Border Router, or ABR, comes into play. It's a specialized router that stands right on the line, literally 1 foot in the local branch area and 1 foot in Area 0. It takes all that local traffic, summarizes it, and smoothly routes it right into the backbone. It perfectly isolates the local databases while still letting data flow anywhere across the globe seamlessly.
So there you have it. You've seen exactly how OSPF takes an absolute routing headache and turns it into a totally automated, highly scalable masterpiece. From using strict bandwidth metrics to brilliantly electing designated routers to scaling globally with areas, it really is a phenomenal piece of engineering. So, with OSPF handling all the heavy lifting of trust, cost, and scale, what massive network empire are you going to build next?